as a recap, this is what we spoke about last week: multi-threading, proof of a function, and then optimization algorithms. So for today, by way of outline, this is what we are supposed to cover. Basically, we are going to talk about graph and graph algorithms, graph traversal, what maximum flow is, all pair shortest path, minimum spanning tree, and how we can decompose a complete graph to the various subgraph that we probably have. And this particular graph is not necessarily the graph that we are familiar with in our basic schools. This is a graph that practically talks about data storage in computer systems. And so when we talk about graph, it is one of the data structures which is mostly made up of vertices and edges. So a graph is a nonlinear data structure which is made up of vertices and edges. And in some cases, we might call the vertices as nodes, and the edges are the lines or the arcs that connect any two nodes in the graph. So in formal definition or mathematical term, a graph is composed of a set of vertices, which is V, and also a set of edges, E, which is denoted by G of E and then V. So if you are talking about computing systems, and specifically we are talking about data structures or algorithm, then if you see something like this G, E, or V, that is the formal definition of a graph. That is to say that every graph should have an edge and a vertex. And the edge are the lines or the arcs that connect two or more vertices, or we could say two or more nodes. So I'll be using the vertices and the nodes interchangeably, but then notice that they are the same in this context. All right. So this is an example of a graph that we have. And as you can see, the lines that connect 0 and 4 are what we call the edge or the edges, and then also the various circles with the numbers in them happens to be the nodes or the vertices. So a graph should contain an edge and also a vertex as well. All right, so moving on, let's talk about some types of graphs. So these are some of the types of graph we have. We have a null graph, we have a trivial graph, and a null graph is known as a null if there are no edges in the graph. So if you have a graph which doesn't have an edge, then we could see that this is a null graph. And practically what we are saying is that if the graph have only one vertex, that is without any edges connecting to it, then you can say that this is a null graph. And then also we have a trivial graph, which is a graph having only a single vertex. It's also the smallest graph possible. So the smallest graph you can get from a complete graph is what we call the trivial graph. All right, so these are some of the graphs that we have. And then we have also undirected graph and then directed graph. And in differentiating between the undirected and the directed graph, we basically mostly use arrows to indicate the flow of the direction. So a graph in which edges do not have any direction, that is an example of an undirected graph. That is to say that you can move from one vertex to the other and from the other vertex to the other without any complications or constraint. Then we could say that this is an undirected graph. However, a directed graph has directions on the edges. So if you look at the diagram below, this is an undirected graph because there's no directions on the various edges. That means that if we are at vertex 3, we could move to vertex 5. And similarly, we could move from vertex 5 up to vertex 3 without any constraints on them. On the other hand, if you look at the second graph here, this one here, from 5 to 3, the edge has a direction, which means that we cannot do the opposite, that we can't move from 3 to 5. So the only direction that we can move from is 5 to 3, 5 to 4, 4 to 1, and 3 to 1. Please take note of it because we are going to use this same concept to understand some other algorithms in the lecture. So undirected graph do not have directions on their edges. Directed graph have directions on their edges. All right, so you could also realize this as a two-way traffic for the undirected graph, where you can move from point A to B and the same way from B to A. However, in undirected, you cannot do that. And then also we have connected graph and disconnected graph. So when we talk about connected graph, when we stand on one node, we can equally visit every other node, or let me say vertices that is found in the graph. So such graph is called a connected graph. We stand at one node, and then from that same node, we can visit any other node that is found in the graph. That is an example of a connected graph. And then we have also disconnected graph. This is a graph in which at least one node is not reachable from a node. So if one of the node is not reachable from the graph, then you could see that this is a disconnected graph. So this example, for instance, is an example of a connected graph. And this is an example of disconnected graph. So when we are at node 5, we could visit 3, but we cannot visit 4 and then 1. That is why this is a disconnected graph. However, if we are at 5, we can visit any other node in the graph. That makes it a connected graph. All right, so let's move on. Now we have what we call a regular graph. Afrifa.
So please, since undirected graph and the what do you call it?
Directed.
Undirected graph and the other graph is having some relationship.
Connected.
Clarify it.
The
Yes.
connected.
Can
Undirected
you?
graph and the connected graph. It seems that
Yeah,
there is a relationship between the two.
I'm not getting the question. Can you come again, please?
I'm asking.
Okay.
When you check the connected graph and the undirected graph,
Yeah.
it seems they look alike.
Yes,
Now,
yes. So in some instances, you might get all the types of graph in one graph. That is acceptable.
okay. Okay.
All right. So this connected graph is the same as undirected graph because there are no directions on the various edges from each node up to the other. All right.
Thank you.
You're welcome. Now we have regular graph as well. This is a graph in which the degree of vertex is equal to k. Emmanuel.
Yeah, yes, sir. Yeah, sir, thank you. And please, I'm a little bit confused as to how to differentiate between the connected and then the
Undirected.
yes, undirected, please. How do I
Okay.
differentiate between the two in case we are being examined on it?
Yeah, so I said that in some instances, you are likely to get the same, various types of graph in the same graph. So assuming that you get this image that I've circled in a question, and you are being asked to produce which type of graph it is. You have two options. Either you go for connected graph or you go for undirected graph. Either answers are correct.
Oh, okay.
Yeah.
Okay.
All right.
All right. Thank you.
Okay. All right. So I was talking about regular graph, and the graph in which the degree of every vertex is equal to k is what we call a regular graph. And when we say a degree of a vertex, we are basically saying that how many edges are connected to a particular node. So let's take this node 5, for instance. Who can tell us how many edges are connected to it?
Two.
Correct.
Two.
Let's take four as an example. How many nodes, edges are connected to it?
5 and 1.
It's also 2.
So that is 2. All right. So it means that how many edges are connected to a particular vertex in the graph? Based on those number of vertices, we can get the regular graph from it. That is why you have here as 2 regular graph. Because for each of the nodes or vertices in the graph, we have exactly 2 edges connecting to each of them. Please, are we clear? Now moving on to the second graph here. How many degree of vertices do you think we have for 5? For this particular vertex 5?
Say 3.
3.
All right, and then 4 is also 3, 1 is 3, and then 3 is also 3. So it means that this particular one can also be called a 3 regular graph. However, based on the previous example we had, we said that for a complete graph, when you stand on one of the vertices, you could move to all the other vertices. So this also qualifies to be a complete graph and also a 3 regular graph. Please, are we clear?
Yes, sir.
So this is a complete graph and then a 3 regular graph. In a sense that when you stand on one of the vertices, you could move to any of the vertices directly without moving through any other ones. This is a connected graph and this is a complete graph. Is I getting the difference?
No.
All right, so we have connected graph and then a complete graph as well. Okay, so now let's move on to in a computer system, how do we represent?
Before you move on, sir, please can you say that the regular graph is also known as the connected graph?
The regular graph is also known as
The
yes,
connected.
you can say it that way. Yeah.
All right.
Okay.
Thank you.
You're welcome. All right, so let's look at how the computer system can represent the various graphs that we just understood. And there are basically 2 ways that graphs can be represented or stored. One of them is the adjacency matrix, and the other one is the adjacency list. And I believe all of us know matrices, right? All right, so let's talk about the adjacency matrix first. So in this representation, the graph is stored in the form of a 2D matrix where we have rows and columns which are used to represent the vertices. And then each entry in the matrix represents the weight of the edge between those vertices. So the first thing you should notice is that the adjacency matrix use a 2D matrix where you have rows and columns. And the rows and columns are for the various vertices. And the edges are going to be the various data points that we have, or the weight on each of the edges that we have. So let's look at this example here, for instance. So who can tell us which type of graph is this? The one I've just circled.
So can we say
I
the
think it's
joints?
complete.
I didn't hear you. John Adu.
There is a
Is a
complete graph.
complete graph. Okay, anybody else? Richard.
Disconnected.
Disconnected. Anybody else? Disconnected, complete. Emmanuel.
Yes, sir. Please, it is between disconnected and complete.
Really? Okay.
Because we have one node
Okay.
connected to all other nodes. And there is one particular, which is 3, not being connected to any of them. Just one, connected to only one. So that's what I think. Thank you.
All right, please, anybody else to help us understand what type of graph this is? In any case, let's understand what a complete graph is. When we talk about complete graph, what we mean is that if you stand on one of the vertices, you can directly visit any other vertex that is found on the graph. So now let's take this example. When we stand at vertex 0, can we go to vertex 1?
No, sir.
Yes, sir.
Yes, sir. You can move to vertex 1.
Can we move to vertex 2?
Yes.
Yes, sir. Yes, sir.
Yes, sir.
Can we move to vertex 3?
No, sir.
No, please.
It means this is not a complete graph. Let me show you this one here. So this is a complete graph. When we stand at vertex 3, we can move directly to any of the vertices that we have. So from 3 we can go to 1, from 3 we can go to 4, from 3 we can go to 5. The same applies to 5. We can go to 4, we can go to 1, we can go to 3. So that makes this a complete graph. But if you look at this example here, that is not the situation here. So this is not a complete graph. However, this is an undirected graph as well.
So I was just about to say it.
All right.
But you didn't say it.
Oh, it just came in mind.
And then also, I think it is also a disconnected graph in a sense that this particular vertex doesn't connect to any other, doesn't connect to this particular one. So in a disconnected graph, at least one of the vertices is not connected. All right, so let's talk about the adjacency matrices. So as I was saying earlier, the vertices are going to be the rows. And similarly, they are going to also be the columns as well. So that is why you have vertex 0 here. You have 1, you have 2, you have 3. And also you have 0, you have 1, you have 2, you have 3. So all that we have to do is that from vertex 0 to 0, do we have any edge connecting to it?
Hello, sir. Sir, excuse me, please. Dominic, your side is giving us feedback, so if you can mute it, unless maybe you're answering the question. Sir. Thank you, sir.
All right. So as I was saying, we are building the 2D matrix. And how we build it is that we set up rows using the vertices and columns using the vertices. So when we are done, we now check to see if there are any edges connecting to the various vertices that we have. Right. So we have vertex 0 and then vertex 0. Do we have a connection or an edge connecting to vertex 0 and 0? This one here.
No, sir.
No, sir.
So since there's no,
It's 1, so there is no other vectors connecting to it.
all right, so that is why it is represented as 0 over here. So vertex 0, 0, there is no edge connecting to it, so we represent that as 0. Now moving on, we have 0 and then 1, which is the 0 and 1. Do we have an edge connecting to 0 and 1?
Yes, sir.
Yes,
sir. That is going to be represented as 1. Now we move to vertex 0 and then 2, which is 0 and 2. Do we have an edge connecting to 0 and 2?
Yes, sir.
That is also true.
Yes,
so
sir.
we have it over here. However, vertex 0 and 3, there's no edge connecting to it. So the weight is represented as 0 as well. Please, are we clear?
Yes, sir.
All right, so one thing you have to notice is that this is an undirected graph, so we can move either ways and it's going to work. So for instance, 0 to 1, we had a 1 over here. Similarly, 1, 0, we have 1 over here. However, if 0 to 1 had a direction, it means that we can move in one direction, we cannot move in the opposite. So if, let's assume the direction is more of this one here, then it means that 0 to 1 is going to give us the 1. However, 1, 0 is going to give us 0 because we cannot move in the opposite direction based on the state that the graph is a directed graph. Bismarck.
Yes, sir. Please, while that's 0 to 1, we wrote 1, and then 0 to 2, we wrote the same 1 there. I wanted to understand, sir.
You say 0 to 1 is 1, 0 to 2 is 1.
Yes, sir. If you look at the table, I want to understand more. So
Yeah, so what we are saying is that wherever there is an edge connecting these two vertices, the weight is 1.
oh, okay, sir. Thank you very much.
So 0 to 2 is where is it? 1 here. And 0 to 1 is also 1. But where there's no edge connecting any vertex, the weight is 0. And then we use that to build this particular matrix over here. Please, are we clear?
Yes, sir. Thank you very
Yes,
much.
sir.
Thank you.
All right. And one other thing, apart from the directions, is that there could be a loop around one of the vertices. So you could have something like this. So it means that from 0, you can come back to 0. In that instance, 0, 0 is not going to be 0, but it's going to be 1 because there's an edge connecting to it. I hope it's clear. All right, so Anderson.
This question, please.
Okay.
And this advancy, this particular thing that we are doing, it's applied to all the types of graph or only a portion of the graph?
Can I get you clear?
I'm saying that this adjacency, right, metrics, can it apply to only the completed complete graph or complete graph, or the only some portion of it?
All right, so it applies to every type of graph. So this is not a complete graph, but then we are able to build the adjacency matrix for it. So you can be given a complete graph, you can be given a directed graph, you can be given a two regular graph, any graph at all. You should be able to follow the same principle we just did to get a adjacency matrix. But then I'm showing you that in some cases, if there are directions attached to the edges, you have to notice them very well. So assuming this is a direction on the edge, then you can move from 0 to 1, but not 1 to 0. In that instance, 0 to 1, the weight is going to be 1, but 1 to 0, the weight is going to be 0. The same way, I also spoke about a loop here. If you have an arc that is connecting a particular vertex, let's say 0, it means that from 0, we can get back to 0. And that means 0, 0 is going to be 1. That is the weight on that particular edge is going to be 1. That is why we earlier spoke about the various types of graphs. So knowing this, the type of graph, will give you the idea of how the matrix is going to be. So if you're given a graph and asked to draw the adjacency matrix or represent the graph as adjacency matrix, it is very important to identify which type of graph it is, especially whether it is directed or it is undirected, because those are going to show you the weight on the various edges connecting the vertices. All right, so maybe before the lecture ends, I'll give you some example and then ask you to find the adjacency matrix and the other one. But then also, you know, students normally say that the teacher will teach you 1 plus 1 and later come and ask you 15 plus 36. That is, they will teach you the easy one and give you the difficult one in the exam. So instead of we giving you the graph to come up with the adjacency matrix, we are going to do the adjacency matrix and I'll ask you to draw the graph.
Since you are giving them a clue of the exams already, of the questions already.
I think this is the Christmas gift.
Madam, you just confirm it for us. Thank you.
I will not confirm. Oh, you. All right, go ahead.
Okay. So if that is the case, then you should be able to draw the graph from the matrix given. Right, so that is that for the adjacency matrix. Now we can move on to the other representation, which is the...
Sir, please, if I may confirm something, meaning that you may be giving the matrix and you may and be asked to draw the graph itself.
Yeah.
All right.
Okay. So let's talk about the adjacency list as well. We are going by the same graph we saw
this one is
earlier.
a follow-up question. So this one is a
Okay.
follow-up question. For example, if you have given the matrix and let's say the matrix is showing the graph of a graph in which the 0 is mapped to itself. How do you notice, or if there's a direction in the graph, how would you know all this is?
Can you come again, please?
I'm saying that, let's say you have been given a matrix, right?
Okay.
And
okay.
this matrix is involving a graph which has a direction.
Okay.
Maybe a one-way direction. How would you fish out that, oh, this matrix is showing a graph that is one direction? Or how would you know that this graph is this matrix is showing a graph that the zero or maybe a vertex is matched to itself?
Okay, so let's take this 0 and 1 here, for instance. So if this is the direction 0 to 1, but not 1 to 0, it means that from 0 to 1 is going to be 1. The weight is going to be 1, but 1 to 0, the weight is going to be 0.
So by that, then it tells you that there's a direction on the graph itself.
Yeah, yeah.
Okay, so sir, please, if I do get it correctly, assuming that where we have
Why are you taking so much interest in this at this time?
please, please, where we have one. So let's assume we have 1 0.
Okay.
The 1 0 I mean, in the box we have 1 over there. So assuming that particular place they have made it 0, so it means that there is no direction within that area. If I do understand it.
Yeah, that is it. That is it.
Thank you.
Yeah. And then so if it's a loop, then you're going to see on the same vertex, you're going to see the weight to be 1. So maybe 0 0 is going to give you 1. That means there is a loop or an arc that is connecting to the same vertex. All right. Now let's look at the adjacency list.
Hello, sir.
Shalom.
Yes, sir. Please, is the numbering always in the direction, or you can just take it to the different direction how you want it? Like the 0 0 moving to 0 1 to your right, then the 1 to whatever. So can I just 0 1 2 coming to down, the 2 coming to the down straight in place of the 3? Can I just direct my 2 there?
I don't get the question, please.
When drawing the graph, right? As you've stated, the 0 1, then you have the 3 under the 1.
Yeah, yeah.
So I'm saying that can it also be 0 1 and my 2 be under the 3 instead of the
interchanging the notes?
Yes.
Yeah, so if I understand you probably want to, you don't want to follow this particular way where you have 0 1 2 3, but then you probably have 0 3 1 2.
Yeah, something like that. I just want to know if this is static. This is how it is.
No. The only difference will be the directions.
Okay,
so
sir.
you don't necessarily have to follow the same pattern, but at least in number system is 0 1 2 3. So it's appropriate you follow it that way instead of mixing the numbers up. John Edu.
Say, please, if I do understand it very clear, the numbers within the box will also be provided, or it wouldn't be provided.
Yes, those are the weights on the edges that will be provided. Yeah.
But I thought maybe it is the one that we have outside together with the one at the top. I thought that is
No.
And the one in the box above here.
Now let me also say this. I think I didn't say that we have weighted graphs as well. So with the weighted graphs, we normally assign arbitrary values to the various edges. And in real life situations could be cost. So we can assume that the vertices over here, 0 1 2 3, happens to be the various cities in the country. And then these edges are going to be the road networks, right? So in that instance, we can attach various costs or distance to the edges. So if you are giving the edges here, the weight on the edges, please write them inside. Because we don't have weight over here, that is why we are using 0101. But then if there are actual weight on the edges, please use those ones. Do you get it? All right, so let's move on. Ampofu.
Okay, so I would want to add to what Salom asked. With what he asked, I think it will depend on where a particular node is connected to. So just as he said that if we can change the two to maybe come under the one, if we are using this very graph, it wouldn't be possible because 2 is connected to 0 and 2 is connected to 3. Or would it be possible? It can it cross over to connect to the 0?
Yeah, so let me say this. The positioning of the vertices doesn't really matter. But as you were saying, one other important thing, if you interchange, you bring the 2 to the 3, it means that your edges are going to cross each other. And that's going to make the graph look messy.
All
Is
right.
that clear? So as much as possible, make sure the graph is drawn cleanly. All right, so for adjacency list, the graph is represented as a collection of linked lists. And then there's an arrow pointer of which point to the edges connect to that vertices. So this is how I represent them. Instead of getting them as rows and columns, please, I'll address your concern very soon. The one who sent the message. Instead of getting the rows and the columns, we just stand on one of the vertices. And now we use a linked list to indicate from 0 which other node is connected to it, which other node is connected to it. And this arrow is the pointer we are talking about. So from vertex 0, we have a connection to 1 and then also to 2 as well. And then also from 1, we have to 0, and then we have 2. And from vertex 2, we can move to vertex 0, vertex 1, and then vertex 3. And then equally from vertex 3, we can go to vertex 2. But as I said earlier, this is going to be different if there are various arrows showing the direction of the flow from, let's say, one vertex to the other. So this is how we represent a graph in the form of a list or adjacency list. Please, are we clear?
Yes, sir.
All right, so with the weight I was talking about, let me give you the real scenario as well. With the weight I was talking about, let's assume that we have these various cities in this country, and the various road networks connecting to them have distance attached to them. So let's assume we have only 4 cities in Ghana. So this is the first one, this is second, this is third, and this is fourth. So from the first to the second, what is the distance? So if the distance is, let's say, 20 kilometers, please just a minute. If the distance is 20 kilometers, that means this is going to be 20. And the 20 becomes the weight on 0 and 1. The same way, if the distance connecting 0 to 2, let's say Kumasi to Accra, is also 10 kilometers, then it means that this 10 here is the weight assigned to this particular edge, 0 to 2. The same way from 2 to 1, let's say 2 is Aflao and then 1 is Boko. The distance could also be, let's say, 25. And similarly, 2 to 3, from Aflao to, let's say, Sunyani, this is also 5. So now these numbers are the weight on each of the edges that we have. So this becomes a weighted graph because we have assigned weight onto every edge that is connecting every vertex or node. John Edu.
Sir, please, I want to ask that looking at what you have on our sheets now, the numbers we have some sort of directions within it. I'm looking at the graph, there is no direction on it. So when we are drawing, if you are giving something like this and we are drawing the graph, so we provide the directions or we should take the directions of it.
Okay, so these are just pointers that are pointing to each of the vertices. They are not directions, to be precise. Look at the text over here, array of pointers. So this one here is not a direction, but it is just a pointer, which points from 0 to 1, 1 to 2. Exactly. Johnny.
Yeah, it's clear now. I want to also ask, is it always that they will provide us with a matrix? Because this one is not a matrix.
No, this is adjacency list. You know, I said earlier that we have 2 ways to represent the graph in the computing system. The adjacency matrix is over there, and this is the adjacency list.
All right, thank you, sir.
Yeah. And yes, let me see. Ebenezer, yes, the matrix table will show or determine how the graph will be shown. That is true. That is why I'm saying that you have to be very careful where you position the various vertices. If you position them wrongly, then you're going to see most of the edges crossing each other to make the graph a lot messy. So only you sketch before you put it on paper. And the same way you can be given the adjacency list and asked to draw the graph as well.
Yes, please, sir.
Shalom.
Yes, this is what I even wanted to ask in addition to. So I just want us to use the list rather to draw the graph.
We should use the list to draw the graph.
Without the graph here, please, I want us to use the list, only the list, to try to draw the graph ourselves.
He's saying that if you can create some sort of a list, then we will try and use it to draw the graph. I mean, try with something like that. That's what I'm trying.
I should give you the list so that you draw the graph.
Yes, we should try drawing the graph with the list, only the list, without the graph here.
Yes, we'll do that later. So remind me if you're about to close, just on 5 minutes.
All right, sir.
All right, sir.
All right, so if we get how to represent the graph, now let's move on to graph traverse.
Question, please.
Christiana.
Sir, please, I want to find out that with the matrix, you said that when it is a weighted graph, we are supposed to use the weight instead of the vertices. So I want to find out whether the list can we also indicate the weight on the pointers to the vertices?
Yeah, I think that will be very clearer. Yes. So if the graph is a weighted graph, you can represent on the pointers. You can write the weight on the pointers. However, if you don't write the weight on the pointers, there's nothing wrong with it.
Okay.
But then I didn't say that in the matrices you write the vertices. I say you write the weight. These are the vertices, and the weight happens to be the weight that are on the various edges. So since we didn't have any weight here, we are assuming that the weight on them is 0 and 1. Please, are we clear?
Yes, sir.
Abudu.
So let's assume that we are given one with weight on it, and let's try to see how we go about it. For example, with this one you have given us, can you put some weight on them, and let's look at how we represent it in the matrix?
It will come later. You combine everything and then do it. So let's move on, please. When I forget, just remind me.
Sir.
Abudu.
Please, the adjacency list graph, it seems I don't understand it, because from two we go to 0, then 1, and then 3 again. Meanwhile, I don't see any vertex, no, any pointer pointing 0 and then 3.
0 and then 3.
Yes.
Do you have a connection between 0 and 3? Do you have an edge connecting 0 and 3?
No, sir.
No, sir. I think
I meant 1 and 3. Sorry, 1 and 3.
You meant
1 and 3.
1.
Do you have an edge connecting 1 and 3?
No.
But the third list, you have 2, 0, 1, 3.
It's rather 2. That is.
Well, please, can I explain to him?
It's
explained to
because when you look at the list,
Abudu, please.
First, second, third.
Abudu, please, let's maybe explain to you.
Okay.
All right. Thank you, sir. Abudu, please kindly look at this one. The vertices are the 0, 1, 2, 3. And we are considering where we have a link between the two vertices or vertices. So when you look at 0, you realize that we have a line linking from 0 to 1 and another line linking from 0 to 2. So it means that from 0, we can have 2 ways to reach 2 different destinations. So from 0, I can choose to move to 1 straight away. Then from 0, I can choose to move to 2. So but with 0 as a vertex, it has 2 particular lengths. Now we have 1 and 2 for 0. Now when I look at 2, let's look at the path through which we can move from 2 to other lengths. Now from 2, we have a line linking from 2 to 0. Then from 2, same 2, we have another line linking from 2 to 1. Then we also have another line linking from 2 to 3. So it means that for 2 alone, we can move to 3 different directions. That is why with the vertex 2, we have 3 assigned to it. 3 different numbers, 0, 1, and 3. Now, when we look at 3, we can only move from 3 to 1 and no other place again because there is no line or linking to 3 and 1 or 3 to 0. So for 3, it is only to 2. So 3 will have just 2. And when we pick 1, from 1, it links to 0. Then from 1, we have another link to 2. So 1, 2 has 2 of these, 0 and 2. So when we pick 3, Abudu, it will only have 2 and not 1 and 0. Thank you.
Okay, thank you, madam. You
Well
know,
done.
yeah, you have done well. In the first place, I was thinking that it's a linear something. When you start from 2, you cannot come back and go to 3. That's what I was thinking. And even I also joined late. That's why.
Abudu, what said is that there can be a graph like this in which there is a direction on it. In that case, when you are following that direction, you can't go back.
That one is linear.
that one is linear. That one goes in that direction in which the graph is showing.
Yes.
All right.
Okay, thank you. That's good.
Please, to add up to what my sister said, the 2, 0, 1, and 3. The arrows over there does not mean that it is even direction. That is what you have to put in your mind. That one I asked earlier on. So it doesn't mean that you have to go from 2 go to 0, then you come back to no. This one is not a directed graph. Thank you.
All right, thank you so much. So just to add on to what Joseph just said, it means that you can actually interchange the position of this in the list. So 3 can come first before 1 and then 0, or 1 can come first, 0 and then 3. Because this doesn't really show the direction of flow from 2 to this. But then ideally, the smallest number should come first before the bigger one. That is why we have 2, 0, 1, 3. Ransford.
Good morning, sir. Good morning, everyone. Please, with what you are really explaining now, that means if it is in a form of a shape, we all wouldn't get the same shape, supposing if you are doing this.
Which shape?
As in adjacent list that we are doing right now, with what you just said.
That
means we will not get the same numbers following.
Yes, so if the order is not the same, but then the same vertices along each of these ones, that is correct. So all of you probably wouldn't have 2013. Some will have 2013, others will have 2310, 2103. That is correct. But then I'll say that at least 2301 is a little bit weird. So the smaller vertices should come first before. But then even in some cases, you might not get numbers like this. 1, 2, 3. It could be alphabet. Is that clear?
Does it mean that if we are given alphabet, we have to go in alphabetical order?
Not compulsorily, but then yes.
All right.
Yeah. All right, so let's talk about graph traversal. And when we talk about traversal, it basically means that moving from one point to the other. Either we are searching for a value or we are just moving through from the beginning to the end. Ampliful.
So, please, I wanted to ask about the weighted graph. So with the weighted graph, what it means is that it can be also either directed or undirected or
yes,
any other, but just that you have the values on them, the weights on them. Okay, thank you.
Yes.
Yes, sir. Please, once again. Hello, sir.
Yeah, we are listening.
Yeah, please. From the list, the third one, I realize 1 is also connecting to 2, connecting to 0, 0 connecting to 1, and 1 is also connecting to 3. But from the graph, I can't see 1 connecting to 3.
How?
I don't get the question, please. You said which one? 3?
When we take the list from the 2
here,
that
did you join late or your network got broken?
Maybe.
Maybe
That's my question. That's my question you're also asking.
Yeah, so maybe it's explain to us. I don't know if you went off a little.
Maybe she should try that side for me again, because
that is after the class, please. After the class, get a number and then she'll explain to you.
Well, the thing is 2. I know 2 is connecting to 0.
Yeah.
0 is also connecting to 1.
Yeah.
And 1 is from the list. 1 is also connecting to 3. But from the graph, that's what I'm getting confused.
Please, it doesn't go that way. What 2 is connecting to?
So this is the starting point.
It is connecting to 1 and it is connecting to 3.
That is all.
Okay.
Yes.
Okay.
And
Understood now.
and to add to a little to it, it said the arrow does not actually show a direction.
The direction, all right, sir.
But rather an array of pointer.
Exactly. So it is pointing to the various nodes that two can be connected to.
Okay. All right, sir. Very well understood, sir.
All right. All right, so when we talk about graph traversal, what we are trying to basically say is we start from the destination, a source, and then we move through the entire graph to the very end. And in the process, we could be searching for a value, or we're just traversing through. So it's more like you moving from let's say Axim to Boko. You're going to pass through several towns and cities before you get there. So that is an example of a graph traversal. So you get to one point, let's say from Axim, you come to Takoradi, you come to Cape Coast. So Takoradi, Cape Coast happens to be some of the nodes. You go to Kumasi, that's also a node. You move to Sunyani, you go to Tamale, in that direction. So each of the towns that we are visiting happen to be the nodes. And that process is what you call graph traversal. But then in the process of traversing the graph, we might want to perform some operations, or we can perform some operations on the graph. So we could either insert nodes into the graph or edges in the graph. We can delete nodes from the graph or delete edges in the graph. And equally, you can search on the graph. And then finally, we traverse all the nodes in the graph as well. So these are some of the operations that we can perform during the graph traversal. We can insert, we can delete, we can search for values as well. All right, so with the graph traversal, what it basically means is that we are systematically visiting each node in the graph. So from one, we move on to the other, we move on to the other until we are done. And this can be tricky because many graphs could have circles or the loops I spoke about, which means that unless we keep good records of the route we take, we can end up going round and round and round in circles. So it is very important that we keep track of the various nodes that we have visited and the ones that we are yet to actually visit. So the basic idea is that we keep a closed list and we keep an open list. So the closed list will give us the idea of which of the nodes or which of the cities have we visited and which ones are left for us to visit. Those are going to be in the open list. And in this graph traversal process, we have two main approaches. One of them is the breadth first search or the breadth first, and the other is the depth first. So if we are performing a search, then we can say breadth first search or the depth first search. But I notice that the strategies or the approaches in the graph traversal are two: breadth first and then also the depth first. So let's take each of them and try to understand it more. So with the BFS, in short, the BFS, it starts from a chosen node, and then we try as much as possible to explore all of its neighbors at one hop away, that is on one level, before visiting all the neighbors at 2 hop away. So in most cases, the graph could be built in a form of a tree, or let's say a family structure, where you have the grandparent, you have the parent, and then you have the siblings in there. So the levels you're talking about here is the grandparents are on one level, you move to the parent, they're also on the next level. They move to the children, they're also on a different level, the grandchildren on a different level, in that particular order. So that's the level we are talking about here. And we said earlier that we have to keep the open and closed list. However, with the BFS, we use the queue data structure for this particular traversal process. And the queue has what we call the FIFO, which is the first in, first out approach. So the first node that is kept in our open list is going to be the first one that will be popped out, or is going to be removed and then explored before we move on to the others. Do you understand the plenty English?
Sir, please, can you go?
Okay, so let's take a practical example and try to understand it. Ampofu.
Sir, please, that's what I was about to say. That if possible, we could take a practical one so that we go through it. That one to understand it.
So let's understand it from this particular graph here. So this is a graph that is being given to us. It has the various nodes 0, 1, 2, 3, 4, right? And then these are the various tools. So when, for instance, the question, if the graph is given to you and asks to traverse using BFS, you will obviously be given a starting point or a starting node, and that is going to help you to move on. So in this scenario, let's take this particular 0 as a starting point. And we say that for the BFS, we explore them level by level. So this is the second level in the graph, and this is the third level in the graph. And we also say that we are using the queue data structure, which means first in, first out. So let me try to see if I can annotate on the graph. Okay. So let's take this one, for instance. We are starting from 0, that is our starting point, right? And then we have the queue here, which is the visited and unvisited. So we could have our list as, let's use O as open and then the close, C as close. So in the initial stages, because we haven't closed any vertices and we haven't opened any vertices, mostly all of these are going to be empty. So this is going to be empty in the start. This is the closing, also will be empty. So this is going to be the first step, right? So in the second step, now we have gotten to this, so we have to now open this. So this is the second step, and in the open queue, we have our vertex 0 in it. So when we open the vertex 0, which other vertices do we see, or can we visit? Anybody?
One and two.
One and two.
One and two.
All right, so it means that in the closed list, we have 1 and then 2 here. Please, are we clear? And mind you, we said earlier that the first in, first out approach means that those vertices that are numbered first are going to be explored or put into the open list first. So it means that if you now get to the next, it means 1 is going to be removed and then 2 will be waiting. All right, so now let's move on to the third. So this is the second step. Now in the third step, we have the open to be 0 and then 1. Because we need to keep track of those we have visited and those we are yet to visit. So 0 and then 1. And now in our closed list, who can tell us what will be in there?
So 2.
So, yeah, 2, 3, and 4.
2 and 3. 2 or 3.
There's 2 and 3.
2 and 3, right? 2 and 3.
All right, so we have 2 and then 3. Right? Because when we go to here, 1 over here, we have the opportunity to now explore 3. Or we can see 3. So 3 is going to be part of the closed list. All right, so moving on to the 4th step. In our open list, we are going to get 0, 1, and then 2. So what will be the closed list? Someone to help us.
3 and 4.
3 and 4.
So we have 3 and then 4. And now we get to the 5th. The open list is going to be 0, 1, 2, 3, and then the close will be what?
4.
The close will be 4. All right. So in our 5th step, we are going to get all our various nodes in the open list, and then the close is going to be empty. So we are going to get 0, 1, 2, 3, 4 in the open list, and then the closed list is going to be empty. Please, are we clear?
Yes, sir. Yes, sir.
Aries.
Yes, sir. Please, I'm very clear with from the second step downwards, but with the first step, I didn't get that one. We have
yes,
and
okay.
everything was empty. I don't know why. Please.
Yeah, so from the starting point, we don't have anything in the open and closed list. So more like, I don't know if you're doing programming, in some cases you declare an empty array. So similar, this is what we just did, so that we can now put in our various nodes we have visited and those we haven't in their respective arrays or queues. That is why the first one, all of them are empty. And the second one, we move on to 0, 1, 2, and the rest.
All right, thank you, sir.
So, if I'm getting you clearly, then it means that we can be given a situation whereby we are told that maybe this node or that node is already visited. Is that the case? So that from the beginning, let's say the first round, we are going to have the open to be maybe 1. Can we have something like that?
Yeah, that is if we want to make you suffer in the exam, right? But but ideally, when you start from fresh, it is easy to move on.
All right.
Yeah. So well, I don't know what Doc will do, but then for let's keep our minds open for anything, right?
So then it means that we'll be glad if you give us a situation whereby, let's say, if from the beginning the question states that maybe node A or B is already visited, so that we look at how you then approach it, sir.
Yeah. So we are not going to speak English in case that is how the question is going to be. We're just going to give you maybe the first and second step and ask you to continue. That's all.
All right. All right.
Yeah. Please, I hope we are clear.
So please, I'm not clear. I beg. It's like I'm trying to grab the whole thing, but it's not clicking. I don't know.
Well, hello, sir.
Hello.
Maybe someone
good
can help.
morning. Good morning.
Good morning.
Some of us, the network problem, so we lost supply. We just joined, so we lost
Yes,
everything.
fortunately, Code Monitor is here recording. So after that, just reach out to them. They'll get it for you.
Yeah, because we lost everything. We just joined.
So
I'll
just do the 1 to 3 steps, and then if you don't still understand, then you can get the videos and watch. Right.
Okay.
The idea is that we are trying to move from one of the vertices through to all the vertices that we have in the graph. And you can be given any other vertex to start from, but then I'm saying let's start from this particular vertex 0 over here. And we are going to use a queue data structure because we want first in, first out. We want to use first in, first out approach. So to begin the process, that is where we initialize our queues so that they will hold the vertices we have visited and those we are yet to visit. And in most cases, we give open and close to our various queues. So we have O for open, and then we have the C for close. And as I was saying earlier, these are empty because we haven't started the traversal process. We are just initializing this so that we can now populate them as at when we start the traversal process. So this is going to be a 0 step. Now with the second step, that is where we start from our root node. And that is the vertex 0. Right. And when we open vertex 0, what vertices are we seeing? We are seeing vertices 1 and 2, which are on the same level. So that means that in our closed list, the possible vertices that we can visit from 0 is 1 and then 2. Now we move to the third step here. Now we have 1 and 2 in our closed list, which means that we haven't visited these ones. So we have to visit 1 first, then 2. So in an open, we have 0 and 1. And then in our close, we have 2. But then when we open or visited 1, we also have the opportunity to visit 3. So that one comes here in our close. So this is the first step, this is the second step, and this is the third step. Now moving on to the fourth step, it means that we have to explore 2. After exploring, we keep it inside the open list. And then we see if exploring 2 give us opportunity to explore another one, which is 4. So we keep that one inside the closed 3 and then 4. So we do that until the closed list become empty. And then we are done. I hope this one here, everybody get it. All right, but let me say this, that in some cases, you might be asked not to traverse the entire graph, but then search for a value. In that instance, as soon as you explore that particular node, you just have to stop the process. You don't have to go through all the other nodes as well. So assuming that we are asked to find this one here, the vertex 2, as soon as we put the vertex 2 in the open list, we are done. We are not supposed to move further again because the value we are looking for is found, and then we have to exit from the code. But then if it is traverse the entire graph, then you have to make sure the closed list is empty before you stop the process. Is that very clear? So that is how the business works.
Sir. Yeah, based on what you're saying, it means the first one, the first example that you did, you ended 5, step 5. It means you have to add 6 to it so that it will be 0. The open one will be 0, 1, 2, 3,
Yeah,
4, and
0.
the question will be empty.
Exactly. Yeah.
Okay. Thank you, sir.
Okay.
And sir, please, with regards to that one, when we are writing the visited as well, can we repeat some of the numbers? Because at times you get 1 and 2, and then you get to 2 and 3, those kind of, I don't know. So when we are writing those numbers within the box that we have over there, that one, can we repeat it as it is, or we should write them once? If 2 appears twice, you have to write it once.
I don't understand the question, please.
For instance, you see, we cited an example that let's move on to you the second step where you wrote 0, 1 from 1, the close one we got that is 3, 2 and 3, right?
Okay.
And I'm saying that if you want to write those values in the visited box that we have here, so that one, let's assume that when we proceeded to the next one, we've seen that the 3 has repeated twice. So in the visited box, are you going to repeat the 3 2 times, or you should write it once? That's what I want to know.
It has repeated twice.
I'm saying that if we proceed to the next step, where you will get maybe 0, 1, and 2.
Okay.
That one, see that you will get the close to be 3 and 4.
Yeah.
And I'm asking that. So if you are writing it, we are fixing it in the box that we have over there.
Okay.
How should we go about it?
Yeah, so the box is just to tell you how we are representing the various visited and then the queue, or the visited on the unvisited. But then what I showed you is what you're supposed to do. So at each step, you add the node you have visited and the ones you have opened in the respective queues. Hello?
Hello, sir.
Please, did you get me?
Yes, sir.
Yeah.
Sir, please, if I get you right, sir, it means
Okay.
that in the visited this thing, you have to write, maybe we have visited 0, 1, 2, 3, and 4.
Yeah.
Okay. Thank you.
But in the solution process, you need to do what we just did. Step 0, 1, 2, 3, that order.
Okay.
So if you want to use what we have here, this is just to show you how it is being done. But if you want to solve a problem using this, you won't be able to represent all of them appropriately. So at each stage, which node have you visited and which haven't you visited? So you have to indicate them in the steps 0, 1, 2, 3, up to the last one. All right, so this is for EFS. And notice we use a queue data structure.
Hello, sir. Hello,
Hello?
sir. Sir, please, can we still go further, or we can just finish on 6? Because what I have here, we have 1, how BFS works. Yeah. We have 1, which is the open and close, which is empty. The open is empty and the close is also empty. So we move on to the second one, which is 0 and 0 for the open and the C for close for 1 and 2. So I'm saying that for what we just did, we ended at 5, but you told us to proceed to 6. So the open is 0, 1, 2, 3, and 4, which the close is. And I'm asking, can we still go further, or when we get to 6, it's over?
Okay, so if at the seed list there is no node for us to explore, so how do you get a node to explore? So as soon as the C is 0 or is empty, that is the end of the traversal process.
Thank you.
All right. So if it is a search, as soon as the node you're looking for is out of the closed list, that is also the end. Because ideally, if you are searching for something and you find it, you don't proceed to be looking for any other thing in the stuff that you have. All right, so this is for DFS. Now let's look at the DFS. The only difference is that the DFS uses the stack data structure and the BFS uses the queue. And we all know how stack really works. So the first one that comes in is the last one that will leave. I don't know if that is true for you, but I mean, that is the truth. Right, those of us who are very familiar with DVDs, when you put in the first one, you have 5 of them, you put in the first one in the tray. It is the last one that will come out later on. So that is the same structure we use for the DFS, as opposed to the BFS that uses the queue data structure. And this is how it works. So we basically traverse in, let me say, the left direction to the very last node. And then if our search is not over, or our traversal is not over, we do what you call a backtrack to come back to the other node that we have not visited, and then we proceed from there. So the only thing you have to notice is that DFS uses a stack, which implement this last in, first out operation. Now let's take an example here and try to understand it. So this is an example graph that is being given to us. And we are asked to traverse a graph from 0 up to 4. So the same, we have to keep our open and closed list to keep track of those nodes we have visited and those we are yet to visit. And obviously the first step is going to be empty, because we haven't visited any node yet. However, with the first step, or let me say the second step rather, we are going to get our starting node to be 0, and then the closing is going to be, so from 0, where do we go? Or which of the nodes can we visit from 0 on the graph?
3.
1, 2, 3.
1, 2, and 3.
1, 2, 3.
1, 2, 3. Okay. But I said earlier that this particular one explores depth-wise in this direction. Right. So that is why we're supposed to use the stack data structure to store our various nodes. So we can assume that these are on the same level, but then the way we put them in the closed list will determine which one comes first. And that is why we are using the stack data structure. So in this sense, instead of 1, 2, 3, we have to do 3, 2, 1, because we are exploring
3,
here.
2, 1.
I'm very happy that you're following. So we have 3, then we have 2, and then we have 1 over here, right? And then the second step, the open is going to be 0, 3, and then when we explore 3, what other node can we visit?
It's 2 and 1.
2 and 1, you sure? This is the graph.
So 2 and 4.
4, 2.
4, 2.
Yeah.
4, 2.
Yes.
When we explore this,
It's only 2.
So
There's
0 to
2 and 0. and 0.
In the depth, it will be 2 and 4. Sorry, it will be 2.
No, 2 and 0.
And 0.
2 and 0.
Yeah. 2-0.
Yes, that is 2-0, but we have visited 0 already, so we will not count that again. So the only
2.
node exactly is 2. However, 2 is already in the list. So we just write 2, 1, and then we proceed. Please, are we clear? So we have.
Sir, please.
Go back to that one again, say.
What I'm saying is that we try as much as possible to avoid repetitions. We have visited 0 already. That was our starting vertex. That's when we got 3, 0, and then 1. And then when we are done, we now move to 3. At 3, we can actually visit 0, but 0 is already visited, so we don't have to go back to it again. What we have to do is now move to the next node, which is 2 over here. So that is why we are having only 2 and then 1 inside the closed list.
Sir, please, why 1, please?
1 is already there, Christ. 1.
Yeah, sir.
I said there is no connecting
There is no connection with the 1 has no connection with the 3.
Yes, but then we have already explored 0 to find out that we can explore 3, 2, and 1. So 1 is already in the closed list. Yeah. So now moving on to the third step, which is 3. Our open is going to be 0, 3, 2. And our close is going to be who can tell us?
1. 1.
You sure?
Yes.
Sir, 4.
2.
4. 4.
4.
Yes, so it's going to be
4 and 1.
Exactly. So it will be 4 and then 1. Please, not 1 and 4. We are trying to visit depth-wise here. So when we get to 2, we now have to visit 8 vertices connected to before we move on to any other vertex. So it's supposed to be 4, 1. And this is the idea behind the stack data structure. What is put in first will come out last. So this one was put in first from the beginning, 1, but it is supposed to come out last. So we have 4, 1, but not 1, 4. And I'll move on to the 4th step, which is 0, 1, no, 0, 3, 2, and then 4. However, at 4, we don't have any other vertex to connecting to it, so we have the close to be 1. And now in the 5th step, we have 0, 3, 2, 4, 1, and then the close is going to be empty. So that is how, Christiana, a DFS works.
Please, it's not Bill.
Oh, Christian, sorry.
You said we are not supposed to repeat, but on the 4th, you still repeated 0 again. But you said we shouldn't repeat any number again.
Yes, we are keeping track of those we have visited, those we haven't visited. So at each step, which ones have we visited plus the one we are currently visiting. So do you get it?
All right.
Any other question?
So please, can you the third and 4th again, please.
Third and 4th and 5th. All right, so but I hope all of us understand from one.
Some of us we are lost. So
Please go over again.
thank you, sister.
All right, so this is the last time we have. This is the last time, so please just shine your eyes, okay? So as I said earlier, the starting point are always 0, 0. So we have the opening to be, empty, and then the close to be empty as well. And now in the second step, 1 over here, our open is going to contain the first or the node that we are starting from. In our case, that is 0. So when we explore 0, we have 3, 2, and 1, or we have 1, 2, 3. But since DFX explores in the left direction first, that is depth-wise, that means that the arrangement is going to be 3, 2, 1, but not 1, 2, 3. If it was a BFS, which is on level grounds, 3, 2, 1 will work, and 1, 2, 3 will also work. But this is DFS, so it's supposed to be 3, 2, 1. So it means that when we go to 0 or explore 0, we have 3, 2, 1 nodes to be explored later. So inside the closed list, that is where we have 3, 2, and then 1. Right. Now in the second step, in our open list, we have 0 and then 3. When we open 3, we have 2 options. So 3 connect to 0 and 3 connects to 2, right? But then 0 has already been explored, so we can't even go there. Or we are from 0, so we are not supposed to go back to 0 again. And then we have 0, which is connecting to 2, but 2 is already in our closed list. So we don't have to repeat the 2. So we 2 and then 1. And then for the third step,
Yeah. Hello, sir. Hello, sir. Question.
Sir,
please, why the 1?
But
Hello,
sir,
sir.
I don't have to repeat the 2 again, but you've written it again,
Yes.
sir.
There is a repetition, but already the 2 is there. That's the question I'm about to ask.
2 is already, so why do I have to repeat it? So I just write what is in there we are supposed to explore. So I'm just repeating what is in the closed list.
So in this case, can I say in the step, you have visited 0, 2, 0, but in the close is going to be 2, 3 or what? Because the 2 is already in the first step, which is 3, 2. The one we have visited already.
Yeah.
Yeah. But why you say there's no repetition, but we are still repeating the 2.
Yeah, so this one already exists.
Sir, if you do understand, those numbers that are in the closed list, it means we have not visited this one. Or
exactly.
Yes. So if you have not, so that is the main reason why you are repeating it, right?
Yes.
Okay, thank you.
No, the repetition I was talking about not to do is that if you have 3, 2 here, you'll be tempted to write 3, you'll be tempted to write 2, 2, and then 1. That is what I'm saying. So if you have the node in the closed list already, you don't have to write it again. In the sense that you don't have to write 3 connect to 2 and then you write it inside here. No. But then those that are not yet visited, you have to add them to the next step.
Sir,
Richard.
Sir, please, the open, the second one, the number 2, the open.
Yeah.
You realize that from 0, you went to 0, 3. Please, why didn't you go to 0, 2?
Yes, because DFX explores depth-wise to the left first, then to the other ones.
Okay.
Yeah.
So no, I'm talking about the open one, not the closed one.
Yeah, so it's 0.3 because if you look at the first one, step 2, sorry, we have 3, 2, 1. So these ones are going to show us which node to explore next.
Okay.
And it is 3.
Okay. All right.
All
Thank you,
right.
sir.
Okay. So now moving on to step 4, we have 0, 3, and then 2. And the close is going to be 4 and then 1, because at 2, we have to explore the depth of 2 extensively before we move on to the other one. So at 2, we have 4 as a node connecting to 2. So we have 4 over here, which is what we are supposed to explore next, and then 1. So if you write 1, 4, it means that you're going to explore this. That brings 1 into the open list. That is going to be an error over there. That is not how the DFS algorithm works.
Because it's last in, last out, right?
Yes, exactly.
Since the one is the last, since the one is the last to be entered in the closed list on the second level, then you have to wait until the one is exited from the closed list last.
Yes.
All right. Thank you.
Okay. And then move on to the 5th step, 4. So we have 0, 3, 2, 4. And then in our closed list, we have just 1. And then finally, in the 5th step, we have the open to be 0, 3, 2, 4, and then 1. Then the close is going to be empty, more like this.
I see.
All right, so that is that for what's the name? BFS and DFS. But as I said earlier in the BFS, if you are asked to search for a value, as soon as that value is inside your open list, don't move on to and stress yourself. That is just the end. But then if you actually traverse the graph, then you have to do everything and make sure that the close is actually empty. And if it is a search, when you get to that particular value and you explore it and put it inside the open list, you are done. All right, so let's move on and talk about some other concept here, which is called the maximum flow. And mostly this is found in a directed graph. This is found in a directed graph. Let me repeat again. This is found in a directed graph. So if you are given a graph and asked to find the maximum flow, and the graph is not directed, however, you still go ahead and try to find the maximum flow, that is your own problem. Just notice that if it is not directed graph, you can write in the booklet that this is not a directed graph, so you can't find the maximum flow in it, and then you are good to go. So in a maximum flow problem, we have a directed graph with a source node, S, and then what we call the sink node, which is T. And then each edge has a capacity, or let me say weight, that represents the amount of flow that can be sent through the network. And we can model this as how our the water from the water reservoirs are pumped into a various house. So from the reservoir happens to be the source node, and then to our various houses are the sink node, which is the T. And whichever tubes that are connecting from the reservoirs to our various node happens to be the edges. And we realize that each of the tubes has the capacity they can hold, the water capacity they can hold. So you can use this same maximum flow to calculate the maximum flow of, let me say, water that can be pumped from the source or water reservoir to a given community that are connected to the water reservoir for the water. And the goal is to find a maximum amount of flow that can be sent from S to T. And in the process, we have to respect the capacity constraints on the edges. So if your tube is 2 milliliters, you cannot pump any water capacity more than that into it. Those are the constraints that we are setting on the various edges or the tube that we have. And with this kind of problem, we use the forward forecasting algorithm to solve that. So we use the forward forecasting algorithm to solve the maximum flow problem. And the whole concept or idea behind this is what we call the augmenting path. And then when we talk about augmenting path, all we are trying to say is that which possible path can we get from the source throughout the whole network to the sink or the destination. So when we get those augmenting paths, we take note of their smallest capacity value. And then when we are done, we add all of them together, and then we have the maximum flow. Please, do we get it? The room is quiet. Am I the only person? Okay, so let me explain using this particular diagram here, right? So let us assume that this is a community setup. This one here is a community setup where people are connected to a water reservoir where water is pumped through the various tubes to their homes. And this one here is the source of the water. And this is the destination of the water, which is the sink. So how can we now pump the water through all these edges here to this particular node 6 without actually breaking the constraints on each of the edges? So what forward forecasting does is that we have to first identify what we call the augmenting path in the flow network, right? So, and then I was saying that the augmenting path are valid path from the source to the destination. So let me identify one of them, and then I believe you can also help me identify some of them. And you have to bear in mind that this is a directed graph, so the flow direction is very much important. So for me, from S, I can move to 2. I'm sorry, from 1 I can move to 2. I can equally move to 4, and then also I can move to 1. So this is one of the augmenting paths. 1 to 2, 2 to 4, and 4 to 6.
Yes.
Who can help us identify another one here?
1 to 3.
From 1
3 to 5.
3 to 5,
Okay.
and 5 to 6.
Then 5
1
to
to
6.
3.
1 to 3, 3 to 5, 5 to 6.
All right.
6.
When you get
2, 3 to 5, 5 to 6.
2 to 5, 5 to 4.
all right, so as soon as you identify the augmenting path, you write a path down, and then you notice the least capacity on the edges. So let me identify the least capacity here and write it. So I have this is 1 to 2 to 4, and then to 6. So who can tell us the least capacity from 1 to 2, 2 to 4, and then 4 to 6?
So it's 2.
It's 2.
It's 2 from 2 to 4.
It's 2.
All right, so we know
That's from 2 to 4.
So that is going to be 2. Do we still have any other ones there? Any other augmenting path?
Yes, please.
So
Yes.
1 to 3, 2 to 5, and then 5 to 6.
Can I be 1 to
2,
1
3.
1 to
1 to 3.
1 to
3
5
to
3,
5.
3 to
And
5,
5 to 6.
and 5 to 6. So what is the least flow?
8.
8.
8.
So we have 8 over here, so plus 8. Now what we have to do is that as soon as we identify the augmenting path and we take note of it, Michael.
Please, can you please come back with that again? How they got an 8?
Yeah, so the path is 1 to 3, 3 to 5, and then 5 to 6. Now the capacities on them is from 5 to 6 is 8, 3 to 5 is 12, and then 1 to 3 is also 10. Which one is the least?
So why 8, 6, and 10?
Why
8, 6, and 10 at the middle?
Why
Do the
8?
Yeah.
Why 8, 6, and 10 at the middle?
Yeah.
No, 8, 12, and 10, they are the weight on them.
Oh, okay.
All right, so the weight on the path is 10, 12, and 8. And the least among them is 8. So besides the augmenting path, you write 8 over there. Because those are what will determine the maximum flow. So we have 8 here, and then we have 2 here as well. Right? But one thing you have to notice is that as soon as you identify the augmenting path and you take note of the least value, we normally call it the bottleneck value. So let's maintain the least value. You have to now update. You have to now update the path. And updating the path literally means that you subtract the least value from all the weight on the edges of that path. So here is going to be minus 8. This is going to be minus 8. This will be minus 8. So now the new weight on the various edges from 1 to 3 is now 2.
2.
3 to 5 is now 4.
2.
And then 5 to 6 is 0.
0.
This path cannot be used any longer.
Confusion.
Please, are we clear? This path cannot be used any longer because it is now 0. Or it doesn't, the path doesn't really exist any longer because we have updated that path.
Confusion, I ever say. Confused super.
Sir, we are lost.
Sir.
Confused. Yeah, I'm confused. Everywhere, everybody's confused. Brothers and sisters, speak that you are confused. So, you.
Can you speak for yourself?
Sir, please, can I ask a question?
Yeah.
Yes, sir, please. Well, the first path that we use, that is from 1 to 2, 2 to 4, and 4 to 6.
Yeah.
The least weight was 2. Why didn't we subtract 2 from all that so that the length there would have been 0? That is from 2 to...
I was coming to do that.
Yeah, okay, thank you so much.
Okay, so now updating the earlier augmenting path 1, 2, 4, and 6. This is going to be minus 2, and this is going to be 6. That's a new weight or the new capacity, right? And this is also going to be 0, which means that this path is not feasible. We cannot use this path any longer. And now this is going to be 8. So when you identify another augmenting path, you are supposed to use the updated capacity or weight, not the previous ones. All right, so let's identify another augmenting path, noting that these ones cannot be used any longer. So anybody to help us?
1 to 2.
1
to
2.
2 to 5. 2 to 5. 5 to 4.
5 to 4 and 4 to 6.
And 4 to 6.
So 1 to 2.
2 to 5.
3. 5, sorry, 5.
5 to 4.
5 to 4.
And 4 to 6.
And then 4 to 6. So on this particular augmenting path, which one is the least value?
4.
4. All right, so we have 4 as the least value here. So we have this is equal to 4. And now we now have to update the path.
There's another one too. There's another one.
Right. So you have to update the path before you look for the other one.
All right.
Yeah. So 1 to 2. Now we have 6. So 6 minus 4 will give us 2 here. So now the mean weight is 2. Right. And now we have 2 to 5, which is 7. This is going to be 3. And this is going to be 0. So this path is blocked. And now this is 8. So this will also be 4. Please, are we clear? Now do we still have another one?
No.
All right. So all right. So now we don't have any further augmenting path here. So all we have to do in find the maximum flow is add the least values, which is these ones. So 8 plus 2 plus 4. That is 14. So we have 14. So for this particular flow network here, given to us, the maximum flow is 4. Please, are we clear?
Please, 14 or 4?
Sorry, 14.
Please, I have a question.
Yeah, Ebenezer.
Hello.
Ebenezer, we are listening to you.
Sir, please, my question is, when we identify the first part, which we got the least weight as 2, why didn't we update the path before we move to the second, before we identify the second path?
Yeah, so ideally, that is what we're supposed to do. So as soon as you identify the augmenting path, you have to update the capacities or the weights before you move on to find some other one.
Okay.
So please, when you identify the path, you notice the least value, update the capacities on the path, and then you move on to the next.
All right. Thank you, sir.
All right. And then irrespective of whichever augmenting path you use, the value of the maximum flow will be the same.
Sir, please, the 14, I might get yours. Can you go over how you got the 14 again?
I should go over how you got the 14.
Yes, please. I noticed that you said we had to add the remaining weights. I don't know the path that we added to go the or we added all the remaining weights. That's what I'm trying to
weight we identified on every augmenting path. So this was our first path, 1, 2, 4, 6, and the least was 2. Now the second path was 1, 3, 5, 6, and the least is 8. The third one is 1, 2, 5, 4, 6. The least is 4. So these are what we are adding to get the maximum flow value.
Okay, thank you very much. Okay.
All right. So that is that for the maximum flow problem. Yes, hello.
Yeah, so is it always necessary to start from the one? Because I'm seeing a path like from 3 to 2 and 2 to 5, 5 to 4.
Yeah, so we said earlier that we have a source, we have a sink. So you have the source, you have the sink. So the source is where you're supposed to start from, and the sink is your destination. So in this example, the source is 1, and the sink is this 6. All right, so let's move on and talk about some other ones, which is the all pairs shortest path. The shortest path algorithm is a method that is used to find the shortest path between two nodes in a graph. And we have two main algorithms that are used to do that. We have the Dijkstra algorithm and then the Floyd algorithms as well. So let's try to understand it. So with the Dijkstra algorithm, it used to find the shortest path from source or any arbitrary vertex to all other vertices in a graph. Please, are we clear? So we use the Dijkstra algorithm to find the shortest path from the source or any vertex to all other vertices in the graph. So given this example, for instance, how do we find the shortest path from, let's take this particular value here as a source vertex? Yeah, anybody who can help us?
To move from 1 to 4,
1 to
6.
2, 4, and 6.
1 to 4 and 6.
Okay, so 1, 2, is it 4 and 6? Okay, so 1,
yes,
2, 4, and 6. So this is going to be the shortest path from this particular up to this particular vertex. So given all these vertices in here, which path is going to be the least if you try to navigate from this to this one? So that is what the algorithm does. So we move from 1, we go to 2, 2 to 4, and then 4 to 6. So this is more like you want to move from here to, let's say, Tamale. And then you have the various cities as a node and the edges as a root network. Do you move from, and then your source is, let's say, Takoradi. Do you move to Cape Coast and then to Accra, then Kumasi, then Sunyani, Techiman to Tamale, or you move from Takoradi, Cape Coast straight to Sunyani, and then? So this is how we mostly do it. So from here, which of the path will give you the shortest distance to your destination? Right, and then also we have the Floyd algorithm. So this also used to find the shortest path between all pairs of vertices in a graph, where each edge in the graph has a weight that is positive or negative. So with the difference between the Dijkstra algorithm and then the Floyd is that Floyd takes care of negative weight. However, the Dijkstra does not take care of that. Yeah, so we are adding the weight to get the shortest path. So this is the weight for 1 to 2, and this, and then this. So when we add the weight here, we are going to get 10, right? Which is the least compared to any other one that we have.
No, sir, please, when we take 1 to 2, 2 to 3, 3 to 5, 5 to 4, and 4 to 6, we will get something like 9.
9. Yeah, 9.
1 to
9.
1
1 to 2.
1 to
2 to 3.
2, 3. 3, 5.
3, 5. 5,
5, 4.
Then
Okay.
4, 6.
And then 4, 6 is 9.
Okay, so
Which is
9.
yeah.
Which will be least.
But that wouldn't be the shortest path.
That is the shortest path. So I did, if that gives you the least value, that's the shortest path.
Yeah, okay. Thank you, sir.
Yeah.
We are adding the weight to get the shortest path. So if the path I've drawn on the screen gives you 9, then that is the shortest path. And as I said earlier, this file doesn't take care of negative values, but the Floyd take care of negative values. However, please, nobody should ask me in what scenario can you get negative values on the weight like this. I don't know. But there's the possibility of
So where are you a
something like
magician?
that.
I'm just about to ask, we have seen it.
Yeah, I know. There are situations like that. There are situations like that. So there are situations like that where you can get negative weight. But please go and find it out. When we meet next week, I'll ask you. Right. All right, so let's talk about a spanning tree. So spanning tree is defined as a tree-like subgraph Solomon, I don't get your question. All right, so a spanning tree is a tree-like subgraph of a connected and undirected graph that includes all the vertices of the graph. A spanning tree includes all the vertices of a graph. This is very much important that you need to notice. The righteous.
Yes, sir.
So the hand is permanently up. Righteous hand is permanently up.
It's not green.
Oh, are you sure? Oh, sorry, okay. So confused. Oh, sorry. Sir, please. Sir,
all right.
Mute yourself.
Yes.
The teacher, could you keep quiet?
Solomon, I'll address your question very soon. So a spanning tree is defined as a tree-like subgraph of a connected, undirected graph that includes all vertices of the graph. You have to notice this. A connected graph and all the vertices of the graph must be included in a spanning tree. And then we could say that it is a subset of the edges of the graph that forms a tree. It means that a spanning tree cannot be a circle. And every vertex or node of the graph is part of the tree. It forms a tree and not a circle. And every vertex or node is part of the spanning tree. All right, so a minimum spanning tree has all the properties of a spanning tree, with an added constraint of having the minimum possible weight among all possible spanning trees. So when we move further, we can talk about minimum spanning tree, where the tree is not supposed to be a circle.
Sir, please, there's a word written on outline on your the screen showing, so it's blocking some of us view.
Outline.
Yeah.
Is it gone?
No, it's not gone.
Outline.
Maybe it's from your end, please.
It's from your end.
Yes, please.
I don't have that.
I don't have that as well.
Say it's okay. It's okay.
Check it.
What are you looking at? All right, so let's continue from here. So please let's notice the difference between or how a spanning tree is. First one is that a spanning tree should have all the vertices of the graph, and the graph is undirected graph, and the graph is a connected graph. Those are what you're supposed to know. And now the spanning tree is a subset of the graph. The spanning tree is not supposed to be a circle. And all the vertices or the nodes of the graph is part of the spanning tree. Now moving on further, we can find a minimal spanning tree, which has all the properties of the spanning tree, except that when you add the weight of that particular spanning tree, it should be the least among all the possible spanning trees that we have. Is that very clear? So when you are given a graph, you can get as many as possible spanning trees in it, but you can get only one minimum spanning tree, except that their values are the same. Then you can get multiple of them. But then you have several spanning trees. However, the minimum spanning tree could be one. So these are the properties of the spanning tree. The number of vertices in the graph and the spanning tree are the same. So in the graph, you have 30 vertices. In the spanning tree, they should have 30 vertices. And then the number of edges in the spanning tree is equal to 1 less than the total number of vertices. So edges is equal to v minus 1. So if you have 12 vertices, the edges are going to be 1 less of the vertex, which is 11. And the spanning tree should not be disconnected because it's a tree. And the spanning tree should be acyclical, or it should not be a cycle. And then when we talk about the total cost or the weight of a spanning tree, is basically the sum of the edge weights of all the edges of the spanning tree. And as usual, there could be as many as possible spanning trees in a particular graph. So let's take this graph for instance. What are the possible spanning trees that you can get from this? So let's try to get some of them. I think this graph is quite easy. So let's start from vertices. Right. So when we give it, we can get C as well. We can get E. We can get D. And then we can get A. So this qualifies to be a spanning tree because it doesn't form a circle, and the number of edges are 1 less than the vertices. The vertices are 1, 2, 3, 4, 5. And in the spanning tree, the edges are 1, 2, 3, and then 4. Please, are we clear? The same way we can get some other spanning trees as well. So earlier on we started from this. Now let's start from C. So we have C, and C is connected to E. E is connected to D. D is connected to A. And then A is also connected to B. So B. So it means that this also qualifies to be a spanning tree. Please, are we clear? So you can get as many as possible spanning trees from this particular tree over here. So now those of you who are math teachers, we want to find how many spanning trees can we get from this. There's a formula that you can use to identify the number of spanning trees within a given graph. So please go and find it out, and then next week.
Yeah, I will say, is it more or less like a tree diagram?
Is it?
Is it like a tree diagram? Or what? I see that like a tree diagram.
I'm not getting you.
I said, you said it's a concept in mathematics. You know, like, is it like a tree diagram?
I said,
as we,
I said the mathematics teachers. Let us find how many possible spanning tree we can get from this graph. And there's a formula to find it out.
I think it should be 5.
It should be 5. Why is it 5?
Because they are to be connected. And looking at how the diagram is, it means each alphabet will start a spanning tree, and the alphabets are 5.
Okay.
So definitely.
Okay, so let's say this one will start. This one also starts. This will start. This will start. This will start. So 5. Please go and find it out. I don't know. But I think it should be more than that. Festus.
Sir, please, I want to ask that can we also have maybe B to A, then A to D, or it is always on the left side?
No. You just have to find a starting point, but make sure it doesn't form a circle. So you can get B to A, A to D, D to E, and then E to C.
Okay.
The only thing is that don't make sure the spanning tree doesn't form a circle. And all the vertices are supposed to be included in the spanning tree. However, the edges should not be exactly as the vertices.
All right. Thank you.
Yeah. All right. So let's look at some algorithms that are used to find this minimum spanning tree. So we have the primes algorithm. They have the Kraskal algorithm. So the only difference between them is that the primes algorithm select vertices with similar weight, smaller weight, sorry. And the Kraskal selects the edges. Kraskal selects the edges, and then the prime selects the vertices. So let's find the minimum spanning tree for this. So if we are going by the Kraskal, which is the vertices, that means we start from an arbitrary vertex, let's say B. So from B, we have vertex A and then vertex C. Which of them has the least weight?
It's A, sir.
So A. So means the next one we are selecting is supposed to be A. Let me use it. So this is our first vertex. So from vertex B, we have C and A, but A has the least weight, so we select this one as well. And now we have A. Keep in mind that we still have C. So A, we have A to D is 3, and then B to C is 2. So which of them is the least?
B to C.
So we select the vertex C. Right? And now we have C and then A. But A to D is 4, and C to E is also, sorry, A to D is 3, and C to E is 4. So we choose the vertex which has the least edge, which is going to be this one here. And then similarly, now we have D to E and then C to E. The one with the least edges, C to E. So we take this. And now we are done. We now connect the various edges to form the spanning tree. So this is the minimum spanning tree from the graph that's given to us. And then when we add this to this, which is 4, this is 6, and this is 10. So we have 10. Unless maybe someone want to tell us that we can still find some minimum spanning tree which has a value less than 10. But as it stands, this is the minimum spanning tree with a total weight of 10. Please, are we clear? So this is how the prime algorithm works. Please, are we clear? So that's how the prime algorithm works. However, if we are going by the classical, we rather choose the edges. Let me clean here. So we rather choose the edges instead of the vertices. So we can choose any arbitrary vertex. So let's start from this particular one here, right? So you are starting from D. So from D, we have edge 5 and then edge 3. We choose the least one, which is this particular edge. And now also from A to B and then D to E, the least edge is this one. So we choose this one. We still have this to compare and then this one as well, this and this. So edge BC and then edge DE, the least one is this one. So we select that one and then similarly this one as well. So this becomes the minimum spanning tree, just as we got for the times algorithm with the weight of 10. Please, are we clear? Any question? All right, so let's talk about the final concept, which is decomposition of graph. And I believe all of us understand what decomposition basically means. Please, you can help us understand decomposition.
This is your screen. I don't know if I'm the only one who cannot see it.
You cannot see it.
Please, hello.
Hello, Abudu.
Sir, based on my own understanding, decomposition means to break something down into smaller units or parts.
Yeah, I think we are done. So breaking something down to smaller component, that is it. So we can close now and then meet next week and continue. Right, but then when it comes to graph, we say that G and then G of 2 are the subgraph if G, G1 is equal to G, where G is the main graph. So given the main graph, you can be asked to decompose that graph into sub components. So basically, graph decomposition is breaking down the graph into edge disjoint subgraph such that this function is true or this method is true. And we have some examples over here that we can look at. So this is the entire graph that's been given to us. And this is how the graph is decomposed. And basically means that if we add this, and this together, we are supposed to get the same graph as this one here. Is there any question? Any question?
Hello, sir. Hello, sir. Hello, sir. Hello, sir. Yeah, sir. Thank you very much.
Okay.
I have hello, sir.
Yeah, listening.
Yeah. To me, I have a personal challenge, but I want to channel it to you to help me. Yeah. I may be pleading after everything you send your slide to us, your PDF to us, because the one we are having is different from what you are having. Though this one, the graphs are not in.
Okay.
By the one we are presenting, we have seen graphs, graphical representation, but the one we are having from the code don't have this graphical representation. So I may plead if you can send this one to us or share it with us, also go through and compare with the one to get better understanding of the course, please.
All right, I've been sending them, just that it comes late. But then today I'll try and share it as soon as we are done with the class. I think I
Okay.
sent it to one of your colleagues. That was yesterday, but today I'll send it to him as well.
And he has not shared with anybody.
It's on the platform.
Place is on the platform. So
It's
check.
on the platform. I
Have
have
not,
it.
you have not been visiting the platform, master.
Teacher, could you keep quiet too?
Please be visiting the platform. I'll send it right away so you won't wait.
Go and buy network.
Oh, 3 or 4 people.
Yeah,
All right,
your
so-
network
so-
is not fine.
So let's see one of the graphs and then, or is it one of the graphs? You said you wanted a matrix and then you convert it to a graph. So let me locate that and then we see. Okay, so something like this. Okay. So please just a moment. I'll get you one on the screen right now. So you can get your pens and then your markers or whatever ready. Richard.
Yes, sir. So because of my network, I was finding challenges understanding the adjacency matrix. Even though I understood the adjacency list very well. So
network.
I want you to maybe allow a colleague that opportunity to explain it like you made Mavis did for the adjacency list. Because
Yes,
for
let
the
us do it.
adjacency
Let
list,
us
I
do it,
understood
right.
it very well.
All right, someone will do that, but then let us go through this before. I'm giving the list so that you can
Hello,
try to
sir.
understand. Hello. Please, I'm listening.
I say you can proceed, please.
Yeah, so I'm trying to now get the things and then share with you. So give me some few minutes. But yes, please, if anybody understand the list, just explain it to him as I find the list for you.
Right, yourself, pass out.
All right, let's go through it. My brother, what you are saying is that the vertices we are having here, right, are nodes which are connected.
Please, not
So,
this one, oh, the previous one, the one that comes before this.
okay.
Let me go back to that place then. Yeah.
With the metrics, what it means is that we are going to use this metrics to represent the flow of the connection between the nodes in this graph. And you could see that in the graph, you could see that we have 0, 1, 2, and 3. From what we just learned, we learned that with the matrix, you use the vertical and then the rows and columns, you present them with the vertices. That's why on the top or at the column side, we have 0, 1, 2, and 3. And then on the row side, we have 0, 1, 2, and 3. So what they're going to do is that wherever there's a link, you use 1 to indicate that there's a link, and then use 0 to indicate there's no link. So you could see that 0 is not, we have only 1 0 here, and the 0 is not matched to any or linked to any other 0. Therefore, on the matrix, 0 and 0 gives you 0. But from 0 to 1, there's a link. So you could see that 0 to 1, we have what? 1 there. And then from 0 to 2, there's a link too. So you could see we have under the 2, we have 1. But from 0 to 3, there's no link. Therefore, we don't have any link there. Therefore, there's 0 under the 3. When you come down to 1, to the node 1 or the vectors 1, 1 is linked to 0. So there's a link there. So you have to represent it with 1. So under the on the row of 1, you see we have 1 under the 0. Then when you go to 1 to 1, there's no other 1 vectors aside the one we're having here. So there's no, and Seth said that there could be a situation whereby there's a loop on the 0. If there's a loop on the 0, then that one, the 1 and 1 will give you 1. But here there's no other connection or link to the 1. Therefore, with 1 and 1, there is 0. And then when you go to 2, you can see that 1 is linked to 2. So under the 2, in the second row, we have 1. And then 3, there's no link between the 1 and 3. Therefore, in the second row and under the 3, we have what? 0. The same thing applies to all the others. When you get to 3, you can see that 3 is linked to, it's not linked to 0. So there's no link there. 3 is also not linked to 1. So there's no link there. But 3 is linked to 2. So under the 2, you have 1 there. And then 3 is also not linked to what? 0. That's what the matrix over here shows. Thank you.
Thank you very much.
Okay, quick question.
Well
Sorry.
understood.
So,
that was an excellent explanation. What's the name of the person who did the explanation again?
Madam, please, my name is David.
All right. Derry, kindly jot his name down for me.
Okay, please, the name again.
David Nikwe.
Okay, all right, okay.
I've typed my name in the message box.
So David.
Okay, all right.
Hey, boys. Hello, David.
Hello, sir.
So you are saying when there is a link, then the figure over there should be 1, right? But when there is no link, it should be 0.
Yes.
Okay. Okay. With the number.
And Seth said that there are times that maybe on the same vectors there is a loop on it, meaning that the same vectors is linked to itself, meaning that on that vectors you are going to have a link to that same vector. Therefore, if let's say you're having a loop on 1, meaning 1 and 1, you are going to have 1 under the inside the vectors at the matrix. And also, Seth said that when you are dealing with, sometimes you may be given a direction in the flow of the graph. So you must consider, if let's say the graph is supposed to flow from 0 to 1, then 1 to 2, and 2 to 3, then it means that you can't move from, when you're on 1, you can't link to 0 because the direction does not go in that direction. The flow does not go in that direction. Meaning that if you are on 1, you can only move to 2.
Okay, so now the next question. You see, there is 1 on 1, but it's 0 over there. Why?
1 on 1. There's meaning that the one we are having over here, we have only one vectors that is labeled as 1. And that one is not linked to itself again.
Okay.
So if you're having 1 and there's no other one, it means that that same one cannot create a link. So there's 0 under it.
Okay. So that's why we have 2 on 2, that the 0, because that same 2 is not linked to itself.
Yes. So you could see that all the vectors are not having any link to themselves.
Okay. Plus 5 marks for you. 5 marks.
Thank you, sir.
Okay.
All right, please
Okay,
let me
so,
make this announcement and then I have to be off from the line. So we are wishing you all Happy New Year. And we wish the course is going on well. From the explanation, from the questions I'm hearing today, I could see that we are on the right track. I'd like you to keep reading the slide and then keep watching the recording. And if you don't get the understanding, kindly reach out to us and form study groups too. I believe when you form study groups, you'll be able to answer all the questions that you want, and then or any clarification can be done to you by your colleagues. So I wish you Happy New Year, and I would have to go off the line right now. So we shall meet, God willing, next week. And if there are any announcements, there we would make it known to you. All right, Derry.
Hello. All right, thank you so much, Doc. All right, so please, this is the adjacency list we have. So kindly help us draw the graph as well. So you sketch it on your paper, and then when you are done, you can walk us through how you did it. I'll draw it for us all to see if it's correct. If it is not correct, then we solve it all together. So you have just
Sir, please,
5 minutes to do this.
can you amplify magnify the screen for us? It seems, or if you can zoom it, it seems that we can see it clearly. So.
Okay, just a minute.
Try to zoom in, it will be okay there.
How do I be zooming?
So we can zoom it on our screen. You don't worry.
I hope it's clear now. This is okay. You have just 5 minutes, please.
Okay, so is I'm done with my end. I want to try.
All right.
Please, can I proceed?
Hello, are we done?
Yes, please. Want to try?
Okay, so someone should lead us. Someone should help us do that. Do the graph.
Okay, so with the graph, this is how I did mine. I had A.
Okay, so
Now
let
for
me relax for me. So we have A.
Yes, please. And I have the C on the right of A.
C to the right, more like this.
Yes, please.
Okay, and
then E beneath the A.
E down here.
Yes, please.
Okay.
And then the D down the C.
D down C.
Yes, please.
Okay.
Then B in the middle of the square in the middle. Yes. That's
okay. B in the middle. So this is B, like this.
Yes, please. And from the pointed arrows in the list, we can see that there are some that are connected and some that are not connected. So this will be a directional graph. Therefore, A will be connected to A will be connected to B.
A will be connected to B
with the arrow. Yeah, with a direction.
With arrow.
Yeah, with a direction.
A to B.
Yeah, then A to C and A to E.
With the same arrows.
Yes, please.
A to C.
A to C and E.
So this.
Yes, please. Then we move to the C. So C will
Okay.
be with the same arrow
Okay.
connected to D.
C connected to D.
Yes, please.
Okay.
And B, but B is also connected to C, so we'll have the arrow pointer facing each of them. B connected to B, C connected to B, and B connected to C. So the arrow pointer.
You have C to D.
Yes, C to D and B to C.
Okay.
So we have the two arrows.
So like this.
Yes, please. Yes. Then we have B to E.
B to E. Okay.
D to E. Yes.
With the arrow or without arrow?
With arrow.
So this. Like this.
Yes, please. I'm done. So
that's all.
Let my colleagues to assess me.
All right. Thank you, Festus. Unless maybe someone has a different thing, tell us what you have. Did you get the same thing? If yours is different.
Sir, why is A connecting to E?
Why is A connecting to E? All right. Did you get a different thing? Francis? Or it's not Francis who asked the question?
Yes, please.
Did you get a different thing?
Yes, sir.
Okay, so let's walk through what you have. Francis, you're not there again.
Yes, please. With mine.
Okay.
A is connecting to B, all right. And B is also connecting to C. And C is connecting to E.
C is connecting to E.
Yes, C.
Okay.
So C is connecting to E.
Okay. Please.
And C
is you let's draw your own.
So my own the difference is that A is not connecting to E.
But then the other ones are correct.
Yes, please.
Okay. Anyways, we will address that very soon. Anybody else with a different graph?
Sir.
McLean.
Me too. It's pretty much the same thing, just that mine to B is connected to D.
B is connected to D.
Yeah. B is connecting to D, and then it's connecting to.
Yes, please. B is connected to D. I forgot to add that one.
Okay.
Yeah.
With the arrow.
Yeah, with the arrow.
Yes.
So
please.
I have a question for you, Ampofu.
Yes,
why the arrows? Why the arrow from C to D?
Okay, so with the one without arrows, let's say the B to C, that one means that B we can move from not B to C and also move from C to B. But with the one with arrows, from A to B, we can move from A to B, but we can't move from B to C, B to A. So in this case, when we look at the list over there, we have B having being pointed to C and D. So B can move to not A, but with A it can move to B. That is the meaning of the arrows for us to know the exact direction of which the node or the path will be.
Please, do you have a different thing?
Yes, please. Okay.
Is having a different thing aside?
Okay. Since I'm not seeing the link between B and C, no arrow, I think I'm cool with it. Like for me, I wouldn't bring any arrow.
From which of them?
Let me see from my angle here. C to D. C to D. So the B to D.
So the B to D, the
Okay.
arrow is pointed to
Okay.
D.
Yeah. Okay.
B to D. The arrow is pointing to B.
D.
Yeah. B.
Okay, so I should reverse the arrow.
Yes, please.
Please, I hope those of us watching, we are fine.
Yes, sir.
No, no, sir.
We are managing. We are managing,
No,
sir.
no. The arrow should be pointed to B, not D. So D is linked to B.
The reason why the arrow is pointed to D is that
There's no reverse.
D isn't linked to node B. When you check the list over there, D is really linked to E, and
E,
B,
yes.
but rather B is linked to node D. That is why we use the arrow. We pointed the arrow to D instead of E pointing to instead of D pointing to B.
All right, I think for now everybody's clear. So if you're not clear, let's.
Sir, no, sir. But per the question, E is E. But
right,
in the drum,
let us all do it together. Let's get the arrows. I mean the vertices.
Sir.
Sir,
My own, I did it. Everything is okay, but maybe with the arrangement. What about if the arrangement is different? Then you have some, like my own A to E. There's some kind of crossing in the arrows. I don't know if you are getting what I'm saying.
No.
Like the arrow pointing A to E crosses that of the C and then the D string.
Yes, it's because you didn't arrange the notes properly.
Yes.
So rather like this one, there's no crossing of the arrows.
Yeah. So in that case, as my arrangement is not proper, but the matching, or let me see the hello.
We are listening.
Hello. Yes,
sir.
For the matching it is correct, but the arrangement is something different from this. With that, in exams, am I correct or wrong?
So in that situation, if the lines are crossing, it will probably mean something else. That is why I said earlier that make sure you sketch it, and as much as possible, make sure the edges doesn't cross each other.
Okay, sir.
Yeah.
Sir, please, can you try to use that to create a matrix?
We should create a, please, that one is an assignment for you. We beg you. All right, so what if
This is
Richard?
Yes, sir. Please, my own too. I realized that they were crossing. The paths were crossing.
Yeah, so make sure the notes are arranged properly. Because it is the connection that will give us a clear view of the graph. So the positions of the vertices are very much important. Yeah. Make sure that they don't cross each other. Christiana.
Please, I want to make some clarification here. Since that is why some of my colleagues are confused.
Okay.
Sir, please, can you zoom the not the graph, the other one?
This one.
The vertices. Yes, the vertices. Okay. Please, the column, the first one, the first that is the vertices.
Yeah.
But the other ones, which is the row ones, they are showing what vertex A is connected to. So with that, vertex A is connected to B, and it is also connected to C, and it is also connected to E.
Yeah.
The same way, B is also connected to C, and the B is also connecting to D. Then when you come to the C, C is also connecting to D, and that C is also connecting to B. Then D is only connecting to E. That is why some of them are getting different graph.
Yes.
Thank you.
All right. Thank you so much. I think we are good to go now.
Sir.
Abudu.
So with this course algorithms,
Yeah.
are we going to apply it in our subsequent blocks or semesters, or after this? That's all.
So computer science, IT is all the courses are interrelated. I think you further make this BFS, DFS in data structures, and you understand they're interrelated. You cannot do computer science without doing algorithms or data structures. Those are very much important things.
Yes, and what I mean is that maybe after this course algorithm, you go and take another course like data structures. So in our courses like software development or C programming, C++ programming, as I was told in this course, when you are coding, will you be using this graph things to code software?
So the main idea.
Application you apply application.
Yeah, so
you apply.
every computing system.
I want all of us to be clear so that you shouldn't do it chew and pour and go and write an exam so that in the subsequent semester you'll be fumbling.
So all
the course it's an ongoing course, so you apply every concept you learn. You build up with.
Okay.
We apply the concept.
All right. So I think we can close and meet tomorrow. Hello. Next week, rather.
The question I asked, it seems I've not gotten answer to it.
Maybe I've forgotten the question.
The arrows.
Yeah.
It's supposed to be having a direction to E, because as we finish this one right now, I intentionally captured the screen and send it to Google Studio AI to draw the node for me. And per the diagram I got, that the A is not pairing with any other node.
A is not pairing with any other node. Yeah, so
node apart from the B.
All right, so as
I didn't say we want to do it with that. So
as Christiana said, these are the starting nodes. So if you are at node A, which other nodes can you connect to?
You can connect to B,
C, and then E.
On the first step, we see A, B, C, and E. So they can connect it.
Yes, let me give you my arrangement.
Remember, the arrow is showing the connection.
So you see, E is not connected to anything. E is not connected. E is not supposed to connect to. E is not having any connection.
Yes. Other nodes are connected to E, but E is not connected to anything.
Yeah, so my arrangement is D in the middle. A, B, C, and then E. I think when we do it that way, we will have the correct graph.
Hello, sir.
So we put D in the middle, and then A, B, C, and then E.
Sorry.
Hello, sir. I wish I could share my screen so that you see the diagram the Google AI Studio draw for me. Then we can take it.
I didn't say want to do it with us.
Okay, then share it. Allow him to share it so that you be clear.
Hello, sir. Sir, please, it seems what you want to share, I have idea about it.
Sister, flow.
That is Christiana, my sister.
Sister Christy, flow.
This.
Sir, so as I was saying earlier on, that the vertices, the first one is determining what maybe the vertices that A is connected to. But with the diagram that he's having here, it means that he made it in such a way that the first one, the vertex A, is connecting to B, and vertex B is connecting to the C, and C is connecting to D. When you do it like that, when you finish, you see that vertex A is only connected to B. But per the explanation given to us when you were presenting, that is not how it's supposed to be. That is why you got that answer.
So and you say that even the edges shouldn't be touching each other or crossing each other, right?
I'm seeing crisscrossing here. They are crossing.
That is what somebody, you see. One thing is that when you are asking the AI algorithm to present you with an answer, you must be sure with the
you need to prompt your prompt.
to prompt
That's
it
something
very
called
well.
prompt engineering. Your prompt
that is it.
determines the answer it gives you.
That is it. So if you don't actually give the correct prompts to the AI, you get any answer. Well, per what you presented, it doesn't show what you have learned.
And who said I didn't give the prompt? I even captured the note that is explaining the adjacent notes and sent it to it. So don't say I didn't prompt it to.
It's not challenging. It's only saying that maybe whatever you put in, that if you don't put it well, maybe it will give you a wrong listen. Meanwhile, I can see that you are using a VPN. I'm sure you are using a VPN data. Share it with us. Let's also use it, brother. Share it with us. Data is expensive. Share your VPN for us.
Share the
link.
Share the link. Share the VPN link.
Don't worry, if you meet for the exams, I'll brief you.
Say it now. Now let us
Sir Francis has been always saying that.
Hello, allow to sum up, and then we can have our conversations around.
Okay. And it's on recording, so make sure you don't say anything.
Sir.
He left.
My brother, can you please let us see the prompts that you gave to the AI? Because I'm also equally seeing it as analyzing the whole nodes and how they are being arranged. Obviously, when you look at it, the other nodes are not linking to A. Probably that is why the AI gave you that visuals. But I would humbly request that you show us the prompts, because AI can be of good at some point too if your prompt is not really detailed to. In any case, you will give us something and then we will argue. Okay, so kindly share with us so that the result will let us know the kind of prompt you give it. Okay.
Why say if you pay
Maybe any network.
All right, I'm back again. All right, so I hope you understand all these. And then from A to E, when we get to the, we don't even have E connecting to any other node, but then we have A that connecting to E. So we can add a constraint and make sure that the direction is only from A to E. So this is for the first list over A. And you can equally move to B as well. So from B to C, E to B. Right. But then we don't have, we have C to B. So that means this can be bidirectional. So we can use this one here. Right. And then also we can talk about B to D, which is this one here. But then we don't have D to B. That means that this is also going to be one directional from this to this. Now we move down to C, which is C to D and then C to B. But C to B is already connected here. So that is fine for us. So now C to D is also one directional. So you pick up this. And then this one also here. Then when we are done, we now move to D, which is D to E. And that is also going to be one directional, but we don't have E to D, so we have this. And then we have this. So this is how this adjacency list can be represented as a graph, as simple as ABCD. So please, if you give it to Google Studio AI and it's giving you no connection to this, then there are two things involved. Either it is not seeing all the various vertices that A is connected to, or the prompt you gave to it, it didn't understand it. So you can further ask it questions and see maybe to give you the right thing. Ransford. The voice is too far.
Okay, sir. With them, there are arrows within it, but from B to C, there's no arrow. So if you can explain that.
Okay, so we have B here, and B is connected to C. When we come to the vertex C, we also have C connecting to B. So that means that at B, you can get to C. Similarly, at B, you can get to B. That is the bidirectional you're talking about here.
So, sir, with the bidirectional, can we use the double arrows, like the one going up and going downwards?
Yes. So if you want to make it very much clearer, you can go for this arrow here. Yeah. So this is also acceptable. All right. So if there are no questions, I'll see you next week.
Okay, sir. All the best of luck.
All right, David. Daniel, sorry. Daniel, we can't hear you.
Sir. Hello, sir. Hello, sir.
Johnny,
Hello, sir.
Please, can you try drawing this one for me? Then you go.
which one?
Hello, sir.
I have some small diagram here. Can we try drawing this and let's see?
Please, let's do it next week. Atanga David, Daniel, please.
Oh, it's very short. It's very short.
Hello, sir.
Just a minute. Just a minute, John. Atanga Daniel.
Hello, sir.
We can hear you.
The directions, that is what I'm not getting. Please, can you go back to the PDF where we're looking at this particular part?
PDF.
It seems like there were directions linking, like showing the connections between the nodes. But then when you were drawing the graph, there was nothing like direction of flow. But here I can see directions of flow in the graphs.
PDF?
Like the one you used to present, the one you use in your presentation.
Let me just a minute. You mean this?
Yes, please.
Okay.
So here we had the nodes being 0, 1, 2, and 3.
Yeah.
So like the adjacency list of the list.
Okay.
You see, from 0, you could there is a connection to 1, and at the same time there is a connection to 2.
Yeah.
When you move to 1, and when you are drawing the list, there was directions there. But when you look at the graph, there is nothing like direction from the connection from 0 to 1 and the connection from 0 to 2. But in the example you just gave to us to solve, in the graph, you indicated directions, like direction of flow.
Yeah.
That is what I'm not getting.
All right, so let's get it from here. Just follow, right? Let's take the first node, which is 0.
Okay.
So 0, we have 0 to 1 and 0 to 2. Is it clear?
Yes.
All right, now let's move to the second vertex, which is 1. So we have 1 to 0, 0 to 1. Look at the first one. 0 to 1 and 1 to 0 means that they are both directions. That is why earlier I did not add the double arrows here. I just use one arrow. This.
Okay.
So this one arrow means that it is BC and then CD. The same way 0, 1 and 1, 0 is the same thing. You can move from 0, 1 or 1, 0.
Okay.
I hope it's clear.
Now I've gotten
the same we have 1, 2 and then 2, 1. So that is it. That is why the constraints or the arrows are not indicated in this particular graph.
Okay.
I hope it's clear now.
Yes, I've gotten that.
Okay.
Thank you, sir.
Okay. Someone else wanted to ask a question. I said you should hold on. I think it's John Adu. You wanted to give us some work again.
So I'm okay.
You're okay.
I'm okay.
We thank God. All right, so I'll see you next week. All the best.
The Holy Spirit has given me the answer. So.
We thank God. All right, so see you next week.
The slides.
Yeah, I'll share it right away.
Okay.
All right, thank you.
So meaning the guy with the VPN has refused to share the link, or
Don't mind the guy. The guy will not go to heaven. The guy won't go to heaven.
Hello.
To share with friends. Won't go to heaven.
Where's Sir Clifford? I think today I didn't see him, or he's sick.
he is an operating system manager for this one.
He is there, pa.
This one.
You are one.
Clifford is an operating system manager. I got a day that is his eldest sister, so you can.
Algorithm is Madam Christiana and Mavis.
Christiana.
Hey, are you sure?
Christiana.
No, we are not sure. We are doing it.
Christiana Yabua.
They are three.
Yes, I'm listening.
Algorithm
You
T.
are using my name. That is why they are calling me Christiana.
Are you the one using my name or I'm the one using your name?
I'm your older brother. I'm Christian Yabua.
So Christian Yabua and Christian Yabua. And this say, I see.
Okay.
Okay.
Okay. So you have to pay me. You have to pay your younger sister.
Chat me.
I hear. I will chat to you.
Charlie, she is married. She is married. You are one.
Oh, my sister, the same name.
She is married. So if you are going there, she is married.
Thank you so much. Don't worry, I'll chat to you.
Those with the VPN, we are still waiting.
We are waiting for the file. We are waiting for the file.
I will send it to you.
I hear
You
my
just
boss.
give us the name on the comment section. Give us the name.
If that's right, the VPN name, we'll download and check it out.
Yeah. So you just send the VPN name. You go and set it and do everything.
Charlie, AI prompt. So one try how I prompt to. Now the way I will be there, you can't tell me.
But I'm like, I was the first Bobo.
Hey, one time AI prompt to no. It seems like Charlie, you me a master you. Hey, I guess that master.
Mr. Fred, Esther.
Esther good
Esther, where is that?
Hey. VPN and Bayana.
Mr. David, so the fire the we are sure say we use VPN.
Yeah, Semu.
Mr. David.
David is gone. Oh.
I think we see.
Yes.
This blood next year. One I'm down. Who is a mature me come and watch you and
Mimum. Really good.
The market crash. Who is that? Some man report do. Yeah, you do remember it, everybody. It's no easy.
Yeah.
Hello, please. Is lecture over?
Please go and start preparing for your next lecture, sir. This one is already over.
All right, thank you.
We have we are supposed to have industrial printing technology too. Those who are not doing mass, those who are doing communication design.